Welcome to section 3.5 exponential and logarithmic models. We're going to solve real life problems using the model y equals y sub 0 e raised to the kt. Each of these values, the y is the final amount, the y sub 0 is the original. You got k as your growth ratio and t as your time. So we're going to be looking at exponential growth and decay models and now be able to solve equations that have the variable in the exponent. So let's go ahead and get started. The first one we have here is talking about phosphorus 32 has a half-life of 14.3 years. How long will it take for 100 grams to reduce to 15 grams? So let's go ahead and set up our equation. We have y is equal to y sub 0 e raised to the kt. What is it that we have? Well, it says 14.3 years, so that must be our time. But that's time for half-life. You know, when we get into how long will it take for 100 grams to get to 15 grams, well, those aren't half of each other. So we kind of have to set up our own initial and final. So you can pick any initial that you want. You can pick 10 grams. 10 grams, half of that you'll be left with 5 grams. You could say 100 grams. Half of that would be 50 grams. You could pick 1 gram. Half of that is going to be 0.5 grams. So you can really pick whatever you want to get started, because no matter what, they're half as long as you do half of it, and the only thing that you're missing is the k value. So this is going to help you find the k value. So those last two pieces of information aren't going to be helpful just yet. We're going to have to find k first and then go back to that. So now we know that I'll just pick the first two here that I wrote down. 5 is equal to 10 grams, except I don't want to write grams. 5 is equal to 10 e raised to k times t being 14.3. How do we solve this equation? Well, we have to get e by itself. So if we divide by 10, we get 0.5 is equal to 1 e raised to the 14.3k. Now, pay attention, because now we're actually back to this last one I wrote down. Because it doesn't matter if you put 150, when you divide, you're always going to get 1 and 0.5. So you can start with whatever you want to get to that value. You could start at this one and then you wouldn't have to do your division. Either way, it's fine though. Now we're going to use natural logs. Because the base is e, we're going to do the natural log of 0.5. The natural log of e raised to the 14.3k, and now that cancels and you're left with 14.3k. Remember, natural log is log base e, so it's log base e of e. That's why that's canceling out. And then now we can divide by 14.3. So we'll get k is approximately, let's find out. We got natural log of 0.5 divided by 14.3. Alright, so we're going to approximate this negative 0.04847, so on. But we're going to actually leave that value in our calculator. So we don't want to lose the entire value of k. So I got negative 0.04847, whatever, approximately. So now we found the value of k. Now let's go back and answer the question that we were trying to answer in the first place, was how long? What is t? What is the time when the initial is 100, the final is 15, and now we know our k value is approximately negative 0.0484. Now we can find the time, because now we have the growth ratio, or in this case the decay ratio. So now we'll set it up again. Now we have 15 is equal to 100 e raised to the, and I'm going to just put k so I don't have to keep writing that decimal, kt. Same as last time, divide by 100. 0.15 is equal to e raised to the kt. Solving it exactly the same way, we're going to have to use natural logs because the base is e. So that will just cancel, and then we'll divide by k. And so our time will be approximately, let's go ahead and plug that in. That'll be natural log of 0.15 divided by the k value. Now I don't want to just write that number down. there's a button on your calculator right next to enter that says ANS. You want the answer to the previous problem. And so now when I use the answer key, I get approximately 39.1 years. So time is approximately 39.1. So how long will it take for 100 grams to reduce to 15 grams? We're just going to say about 39 years. And there you go. So it's kind of a two-part problem, but in both problems you're solving for the exponent. This one you're solving for the k value, which is in the exponent. This one you're solving for the t value, which is in the exponent. So that's a decay. Let's go ahead and look at a growth. A bacteria doubles every 45 minutes. How long before fivefold? Fivefold just indicates that you are starting at, let's say, 1, and now you're getting 5 times that. How long does it take you to get to 5? So let's once again kind of set this up, see what we have. We have the equation. The final amount is equal to the initial amount, e raised to the growth ratio, times the time. So what is it that we have? Well, we have that the time is 45 minutes. But this time only indicates how quickly that a bacteria is doubling. So we know it's 45 minutes. The initial amount and the final amount, just like half-life, you can kind of create. If your initial amount is 1, then your final amount is 2. If your initial amount is 2, then your final amount is 4. So you get to pick, which one you want to kind of set it up as. So we'll do the same thing. The y, we'll say is 2, we'll use the first one, is equal to the initial, which is 1, e raised to the kt, so that'll be 45 times t. And normally we would divide by whatever that number is if you would have chose 2 and 4, but because it's a 1, we're good to go. We actually can go ahead and do the natural log. So we'll do the natural log of both sides. And I'll write it this time, but realize natural log of e is just going to cancel anyways. So we have the natural log of 2 is equal to 45k, and then now we can divide by 45. So we have the natural log of 2 divided by 45. So let's do that. Natural log of 2 divided by 45 is 0.0154 approximately, 0.0154. So let's write that down. And we're going to keep it in the calculator, so that's approximately what it is. And then now we once again kind of set up our second equation to this one. We want to know how long it takes to get, something fivefold. So time, we don't know. That's what we're solving for. The initial and the final, well, let's say the initial is 1, that means the final will be 5. The initial's 2, the final's 10. However you want to do that, and then we'll do the k value, which we do have from what we just found. So we have 3 out of the 4 pieces, so let's set it up. 5 is equal to the initial, e raised to the kt, understanding that we do have the k value here. So we'll do the natural log of both sides. That will cancel out the base of e. And then now you can divide by k. So we'll take the natural log of 5 divided by k. Natural log of 5 divided by second answer, the answer from above. Do not approximate it. And we'll get 104, I think this one's in minutes, yeah. Approximately about 104 minutes on this one. So t was approximately 104, I think 0.5 minutes or whatever. So we'll say, to go from 1 to 5, 2 to 5, 10, fivefold, it takes about 104 minutes. Because I think it was 104, I put 104.5, but I was thinking, yeah, it's 104.48, so we would round 104. So approximately 104 minutes. And so there we go. And that makes sense. Think about it. To go from 1 to 2 would be 45 minutes. To 2 to 4, if we're thinking if we start at 1, we go to 2, that would be 45. 2 to 4 would be another 45, so we're about 90 minutes. And then from 4 to 8 would be another 45 minutes, but we're only trying to get to 5. So somewhere in between, you know, this is going to be 45, this is going to be 45, and this is another 45. So somewhere in between that 90 and 135, which is 104 where we're at. So it makes sense to the problem. Alright, here's the last example. Kind of a lot going on here. I should maybe do this one in class with you guys so you guys can kind of see how this works out. Why don't I do that? I'll do this one in class with you guys, and we'll kind of go through the process on this one. This one takes a little bit more explaining and a lot more going on this one. If you want to give this one a try, there's definitely a couple different questions that you have to answer. So just stay organized with it. Take a look at the notes when you're done, and you'll see if you got it right or not. And then the rest of you, I'll definitely talk about this one in class. But from what we did on the first two examples, this should really give you guys enough to work on the homework. I just really like this one. This one's we say real life, but this one's a pretty good one. So go ahead and do your homework, and we'll talk about this one in class.